So, hi everyone. 9.2, 9.1 was all about an introduction to hypothesis testing and what it is. So, we use it to test to see whether a claim is valid or not, if we have convincing evidence to support the claim or not. So we talked last time about how to write a hypothesis. We said the null always has some type of an equal sign, and then your alternative is going to be the one that has the less than, the greater than, or the not equal to symbol. We talked about did we talk about conditions? I don't think we did. We talked about p-values, not how to compute them, but how to interpret them. So if p is small, you reject the null. We've got words to use. So I believe we also talked about some errors, and we said, sometimes a significance test could make a mistake depending on your alpha level and stuff like that. So that's where we were last time. So we're going to get right into a hypothesis test today. So we're going to do a full hypothesis test start to finish. So we're going to start with proportions just like we did in confidence intervals. You have your conditions. They shouldn't be a surprise. They will always be the same. Just sometimes how you check them is different. Random is always the same, obviously. Does it come from a random sample? 10% is always the same. So again, I always use this one over here. So 10 times n has to be less than or equal to the population. I think most of you have probably caught on that what I say is I do 10 times n, and then I say assume that there are that many items in the population or that many people in the population. And then large counts. Now large counts is different depending on if it's a mean or a proportion. Remember mean, we've got that magic number of 30 or it can't have any strong skewness, that kind of stuff. But for proportions, it's always this n times p and n times 1 minus p. For this one, you do have to be careful because you're not using your sample proportion, you're using your hypothesized. I think I just spelled that wrong, but hypothesized proportion. So right from the hypothesis is where we will get those numbers from. The same thing with that p sub 0 right there, and they have to be at least 10. We will be finding a test statistic. So we will find a test statistic using this formula right here. This is pretty generic. So this is going to be for both a mean or a proportion. If you want the more specific one, then I think it's later on. We will be doing a one sample z-test. That's the name of it. We still have our state plan do conclude. State, what do you want to test and at what significance level? You need to put your hypothesis, you need to put your significance level, and you need to define any parameters used. There's 3 things that need to go into that state plan. Please make sure you name your test. That's what this first line means, this choose the appropriate inference method. You have to name your test. If you do not name your test, you will get points off. And then to check the conditions, and then you're due slightly different than before. You're going to compute your test statistics. So that's using this generic formula. And again, I'm going to show you the more specific formula in just a moment. You're going to find the p-value. To find a p-value for it's a probability. You're going to use normal CDF, and then depending on what's in the alpha or the look in the alternative, and then that will tell you whether it's a less than or a greater than, and then that will help you to decide what numbers go in your normal CDF. And then your conclusion, and make sure you put your conclusion in context. Now, before I go any further, I would like to mention that you have these reference papers. I've given you all a reference paper at this point, hopefully. So on the front is all of your formulas. By the way, there's that generic formula that I was just talking about. That's right there under inferential statistics. But if you scroll to the second page, so before what we were doing is we were doing these estimates. So right there's the estimates. This is for a confidence interval. Today we're going to be starting our proportions and our test. So right there is going to be the specific test statistic. There's the name of our test, and then over here are those conditions that we just mentioned. And if you scroll up a little bit, if you see over here on the side, it tells you exactly what to put in the state plan do conclude. So in the state, what hypothesis, and what significance level, and define your parameters. Choose the appropriate inference method. That means name your test and check your conditions in the plan. Do compute your test statistic and find your p-value. Again, the test statistic is this part right here. So you've got your p hat, that's your sample proportion, minus your hypothesized proportion, and then over your hypothesized proportion, the standard deviation of that. After that, you're going to do a normal CDF to find your p-value, and that information you will get from the alternative hypothesis, and then you're going to interpret. So it's all right here on this reference paper. Keep this handy because it's a very, very good reference. Okay, so there's that test statistic I was telling you about. I told you I'd make it more formal. It's on your reference paper, so no need to copy it down unless you just want to know it. I am going to break down the pieces for you. When you see p hat, that's your sample proportion. So that's when you do the experiment. So let's say you've got a sample of 300 people and 20 of them say vote yes, something like that. So that 20 out of 300, that's your sample proportion. When you see that p sub 0, that's your hypothesized proportion. And that's going to come from your hypothesis. Okay, now that one right there is also in the denominator. So you only use your sample proportion once. Okay, now the next piece, so that's pretty easy. That's just typing it on the calculator. So this is in the do portion. You find your test statistic that's a z-value. Now we need to figure out our p-value, which is the probability of being in one of these regions right here. And the important note here is that you have to look in the alternative. So if you look in the alternative, so if you look right here, this first one, in the alternative, there's a greater than symbol. If you see a greater than, then you plot your z-value, which we've done right there, and you shade to the right. This is called a right-tailed test. Okay, because you're shading to the right. If you see a less than in the alternative, then you plot your z and you shade less than. This would be for less than, and this would be called a left-tailed test. Okay, now both of those are one-sided tests because you're only finding the probability of being greater than or less than, not both of them. Now, if in your alternative there's a not equals to, so what you're saying there is you're not asking whether, let's say, a certain proportion of the people is less than what's predicted or greater than what's predicted. You're just saying it's not what is predicted. So it's not equal to. Then we call this a two-sided test. Okay, so these two over here were one-sided tests. This one over here is a two-sided test. So two-sided test, one-sided test. And again, you get that information by looking in the alternative. So in the alternative, it's greater than, shade greater than, and it's a right-tailed test. If it's less than, then you shade less than, and it's a left-tailed test. If it's not equal to, you plot your z's, and you shade both less than and greater than. So to find your probability here, all you do is find the probability of being in one of the regions, and you multiply it by 2 so that it's in both of them. Okay, so here's a full test. I think I do 2 of these, and then I think that's it. So let's read through this one really quick. We've got it's like an American Idol, a singing show, and they want to know if there's an advantage to going last. So to do this, what they said was there's 12 singers, and then they would expect that if there is a preference for the last person, then the last person's probability would be greater than a 12th. So think about this. If everybody has an equal chance of being selected, equal chance, it doesn't matter whether you go first, in the middle, or last, then out of 12 contestants, the probability would be the same. They would all have the same probability. So the probability of the last singer winning would be a 12th. If there's a preference, so the last singer does tend to be picked more often, then the probability should be greater than a 12th. Okay, now right now, just by looking at this, just because it was on that previous page right there, if you look in the alternative, I already know that I have a right-tailed test here. And that's because if I sketch my normal curve, I'm going to find a z, hopefully it's over here on this side, and there's that greater than symbol. So I'm going to shade greater than, which is off to the right. Okay, so just keep that in mind just because that was the last thing that we talked about. So now let's talk about state. In state, you need to state your significance level, your hypothesis, and what your p is. My significance level is 0.05. By the way, if they don't tell you a significance level, use 0.05. My hypothesis, remember in your hypothesis, you always have an equals in the null, which means that the probability is the same for all the contestants, so p equals a 12th. And in my alternative, I'm saying that the probability for the last person is greater, because if there's a preference, they have greater than a 1/12th probability of being selected. So the greater than would go in the alternative. And then I have to, so there's my hypothesis. And then lastly, I need to say what my parameter is. So my parameter, in this case, the proportion, is the true proportion of students who prefer the last singer. In your plan, you need to name your test, so right there, one sample z-test, and then you need to check your conditions. It is random. It says up there that it was a random sample of 600 college students. 10%, you do 10 times your sample, so 10 times 6D, which by the way is not 3,000, but is 6,000. So we assume that there are more than 6,000 college students, which I think that's safe to assume. And then lastly, you need to check your large counts of your normal condition. So you do n times p, so 600 times a 12th, which is 50. And then you do n times 1 minus p, which is 600 times 11 twelfths, which is 550. Notice both those numbers add up to 600. Both of those numbers are greater than or equal to 10, so we can assume that they're normal. And again, in case you ever forget, all those conditions are right here. Random, normal, and then independent. Okay, and just one thing to point out, notice that they're saying to use for the normal condition your hypothesized proportion, not like we haven't even started to use our sample proportion yet because it's actually a little unethical. I mean, not really, but kind of. You want to set everything up before you collect your data because otherwise you might sway your hypothesis if you collect your data first. Okay, the do. First thing I need to do is find p hat. I don't like leaving them as fractions. I guess you could. But my p hat is 59 out of 600, and that came up from up here. So it said 59 out of the 600 students preferred the last singer that they viewed. That gave me a sample proportion of 0.098, and that is right there. Now, the rest of the equation is all off of the hypothesized proportion, which is the 12th. So you do the 0.098 minus a 12th over the square root of a 12th times 1 minus a 12th all over your sample, which is 600. And then the worst part is typing that in on the calculator. And if you do that correctly, you should get a z value of 1.2998, which again matches my picture up here. Okay, so then once I have that, I'm going to find the probability of being in that region right there, and that's my p-value. So that's like assuming the null is true, that it is a 12th. Let's see what the probability is of getting the sample data that we did. These should be labeled, so we know that this is my min, this is my max, this is my mean, and my standard deviation. And notice that this is standardized because we found a z. A z-score is a standardized score, so I'm going to leave that 0 and 1. Now this one should not be multiplied by 2. That one, I think the answer is right, but should not be multiplied by 2. It's not a two-tailed test, so you just find that one region right there. May have done a little copying and pasting from the next question. So I get a p-value of 0.0968 just by typing that in on the calculator. And then to conclude, again, use my words. You'll get really used to using this. But anyway, since p is greater than alpha, right? P is 0.0968. And alpha is 0.05, so the 0.0968 is bigger since p is greater than alpha. P is not small, so we fail to reject the null. Fail to reject the null is another way to say you don't have convincing evidence to say that the alternative is correct. Always go back to the alternative when you are interpreting. Okay, so we do not have convincing evidence that the proportion of college students who prefer the final singer is greater than a 12th. We do not have convincing evidence that there's an advantage to going last. So always go back to the alternative. Do you have convincing evidence for the alternative, or do you not have convincing evidence for the alternative? In which case, since we failed to reject the null, we do not have convincing evidence for our alternative. Okay, and then this one right here is our last hypothesis test. So you can read through it, but basically it's an accounting firm, and they're saying that they would do a special audit if they find that the proportion of first digits that are 1 should be 30.1% of those numbers, of those accounts or whatever they're called, there's financial records. If they find that it's not 30.1% of the accounts that start with with 1, then they will do that special audit. Okay, so that leads me down to my hypothesis here. So if you look at my hypothesis, the first one says that the proportion, or the true proportion of expenses, P is the true proportion of expenses that begin with number 1. It's either equal to 0.301 or it's not equal to 0.301. So it didn't say anything up here like if the proportion of expenses that begin with the number 1 is less than 30%, we do the audit, or if it's greater than 30.1%, we do the audit. It's if it's not 30.1%, then we do the audit. Okay, so that's why that is a not equals to. So this one right here is what we would call a two-tailed test. In a moment, we're going to do our sample, our test statistic. We will only get one value, but it's symmetrical. So whatever we get, we're going to put on here twice, once in the positive, once in the negative, and we are going to find the probability of being on the outsides because it's not equal to. So it's not just this region, it's not just this region, it's both of those regions. So a two-tailed test. Okay, so read through that state. The plan, the same thing as before. I've got the name of my test, one sample z-test, random sample of records, it set it up there, 10% condition, 10 times 300 equals 3,000. So we have to assume that there are more than 3,000 records. And then I think I might have covered that up. Sorry about that. But basically, this part down here is my normal condition. So what I did, go back to the 0.301. We chose 300 records. So you do 300 times 0.301. And we need to just check to make sure that that's at least 10. It's equal to 90.3. And then I did do the opposite, so you can see that right there. 300 times 0.669, which is 1 minus 0.301, is equal to 209.7, which is also greater than or equal to 10. So because they're both greater than or equal to 10, we can assume normal. If you forget, go to your reference paper, and there's those conditions right there. Notice I'm still using the hypothesized proportions. Okay, so next I'm going to start to figure out my z statistic here. So that's p hat minus the hypothesized p, and then everything else in the denominator is based off of the hypothesized p. So that's over here. I found my p hat. I think they said that there was 68 out of the 300 expenses that began with the digit 1, which gave me a sample proportion of 0.2267. Remember, you only use that once. That's right there. The rest of the equation is based off of the hypothesized proportion, which is the 0.301. Typed it in on the calculator very carefully. By the way, that bottom number is 300 because that's an N. You should get negative 2.79, so that would be that line right there. And that means the upper one, because it's symmetrical, is just the positive 2.79. So now you need to find the probability of being, and what I do is I just find the probability of being one in the regions, and then I multiply it by 2 to figure out the probability of being in both regions. Now, just to point out here, because we have talked about this quite a bit, you are almost 3 standard deviations away on both sides. 3 standard deviations. If you remember, if you're 2 standard deviations away, remember when we did the normal curve and we said, okay, if you're 2 standard deviations on either side, that's 95%. right? So that leaves 5% for the outsides. So now we're even further over. So three standard deviations is actually 99.7. So you can also kind of check your data. So if there's 99.7% in here, that means there's a very, very low percentage to be on the outside. So you can talk through that, or you could do the normal CDF. Make sure that you label your inputs. So minimum, max, mean, and standard deviation. This one is times 2 because again it's a two-tailed test, and that's because that's a not equals to right there. It gave me a very small probability of 0.0053. Since p is less than alpha, again that p is the 0.0053 and your alpha is 0.05, so p is less than alpha. If p is small, we reject the null. So if you reject the null, that means you do have convincing evidence to support the claim that the proportion of expenses that have a first digit of 1 is not the 0.301, which means that they should do a more thorough audit. Now, circling back around, I know this is kind of a long one, but we've got a lot going on right now. So what I did on this one, you can probably just read through it a little bit, but this is the same question, but I just did an interval instead of a hypothesis test. They should tell you the same thing. The difference is a test tells you whether a value is plausible. And confidence interval gives you a range of plausible values. So a little bit more data, I think, comes from a confidence interval. So same question. We wish to estimate the proportion of all expenses that begin with a 1. At 95% confidence. So then we're going to do a 1 sample Z interval. I already said the conditions have been checked. They're the same as before. I think you do have to check the sample proportion for this one, but believe me, it will work. All of the information is there. Just make sure that you pay attention to that. Went through the work. I got an interval of 0.173 to 0.274. Now remember, the proportion for a more thorough audit is if the digits are not equal to that 0.301, or the proportion of expenses that start with a 1 is not equal to that 0.301. Well, in case you didn't notice, 0.301 is not in our interval. So that means it's not a plausible value, which means that the company should do a more thorough audit. So you can read through this at your leisure, but basically this says the exact same thing as the hypothesis test. So if I could give you one piece of advice to finish up this 9.2 video, please become familiar with your reference paper because it's all right here. Okay, so we're going to be working in proportions. It's a 1 sample proportion and we're doing a test. If you look up here, it tells you exactly what to put where. Probably the piece that's a little tricky right now is just writing the hypothesis. So is it a greater than or a less than or a not equal to in that alternative there? That's probably the worst part, and then typing it in the calculator. The rest of it is all given. Okay, so that is it. So we will practice this in class, and hopefully by the end you'll be really, really good at hypothesis testing for proportions.